Hello everyone, and thank you Kelly for hosting this webinar. My name is Eduard Cojocea and I'm the CTO of Esenca Sizing. And today I will talk about what more than 500,000 body measurements reveal about women's workwear and PPE, and how manufacturers, employers, and digital solution providers can work together to improve fit and protection, particularly for women where some of the largest gaps remain. Now for the contents. I will begin with the challenge of women's PPE and explain why dedicated women's collections are necessary. Then I will show how AI-based body measurement works and how individual measurements can support sizing decisions at scale. After that, we will look at population anthropometry and some of the patterns visible in our data. Finally, I will bring these ideas together into a practical vision for the future of women's PPE. Now, going to the first section. The core problem is familiar. Women's workwear and PPE are still often based on unisex collections or on men's collections that have simply been scaled down and adjusted slightly. There has been meaningful progress. Women's PPE has improved significantly over the past several decades, and a growing number of companies are investing in dedicated women's workwear. Nevertheless, the problem remains widespread. Many women still struggle to obtain garments that truly fit their bodies. Why fit matters? Before discussing the technology and the data, it is important to define why fit matters. In factories, industrial plants, and many other workplaces, people must perform a wide range of movements, like reaching, kneeling, climbing, lifting, and working overhead. Workwear and PPE must allow this mobility while continuing to provide the intended protection. A successful garment, therefore, has to support safety, comfort, productivity, and user acceptance at the same time. These points may seem obvious, but as an engineer, I find it useful to define the problem clearly before discussing how to solve it. Moving on to the next slide, we are talking about full body PPE. The need for protection is not limited to garments. Handwear and footwear also play essential role. In some industrial environments, gloves and footwear may be even more critical than the clothing itself. Workers may handle hazardous chemicals, for example, or work around heavy objects that could injure their hands or feet. For that reason, we need to consider PPE as a full body system. Fit matters across garments, gloves, and footwear, not only in jackets and trousers. Poor fit is not merely an inconvenience. It can restrict movement, create snagging hazards, cause discomfort, and, perhaps most dangerously, reduce a worker's willingness to wear PPE correctly. If PPE is uncomfortable or interferes with the work being performed, some workers may loosen it, wear it incorrectly, or remove it altogether. And at that point, a fit problem becomes a safety problem. Why is this difficult? Why does women's PPE remain so challenging? Women have enormous diversity in body shape and proportion. They may also have different job requirements and garment preferences. Preference, may sound less important in a PPE context where protection must come first, but it still affects user acceptance. People wear these garments for many hours, so they need to feel comfortable and confident in them. Many of the size charts are built around the concept of an average woman. In practice, there is no single average body that adequately represents the entire population. One size system cannot represent everyone. What I'm saying is that no size system can represent every person perfectly. This is true for both men and women, but it's particularly visible in women's workwear. Well, traditional size charts rely on clusters and population averages. They necessarily place many people into the same category, even when those people have meaningfully different body proportions. Two women with the same height and same weight may still require different garment sizes because of their chest, waist, hip, and other measurements can differ substantially. And height and weight alone, therefore, do not provide enough information for accurate size recommendation. Now, moving on, traditional sizing has limited information. Traditional sizing usually begins with a small set of measurements such as height, chest, waist, and hips circumferences, for example, and these are important measurements, but they are often insufficient to describe the diversity of real body shape. And traditional workwear deployments also commonly rely on in-person fitting sessions. A representative travels to a factory or company with a physical size set and asks each worker to try on the garment. And this can take 15 to 20 minutes per person, or sometimes it can take even longer, which severely limits how many people can be fitted in one day. The physical fitting set can introduce additional problems. Because of repeated washing and use, some of the garments may shrink, stretch, or otherwise change shape. And the most common middle sizes are usually tried on the most often, so they may diverge the furthest from the original specification. Eventually, the physical garments may no longer match the official size chart consistently. There is also a more fundamental limitation. A few standard measurements cannot always capture the part of the body that actually determines fit. For example, I'm a big guy and I am 6 feet 4 inches tall and weigh roughly 240 pounds. In my case, the problem is often not my chest or waist, it is my shoulders. To obtain enough room around my shoulders and armholes, I sometimes have to choose a jacket that is unnecessarily loose around my chest and waist. And the limitation of size charts are universal, but women encounter them particularly often in practice. Now, moving on to section 2. Women are not simply smaller men. This brings us to the second section and its central point. Women are not simply smaller men. The assumption is not necessarily made in bad faith. Scaling down a proven men's collection may appear to be a reasonable shortcut. The data, however, shows why it does not work. Even when a man and a woman have the same height and weight, their body proportions can differ significantly. There are differences in body shape, center of mass, and the distribution of lean mass and fat mass. These biological differences appear clearly in the anthropometric data that we will examine later on. Now, body shape matters more than overall size. Overall size is not the same as body shape. A woman may fit within the same overall volume as a man and still require a very different garment pattern. Imagine placing the torso of a man and the torso of a woman inside the smallest possible enclosing cylinder. Even if those cylinders were identical, that would not mean the two people should wear the same garment size. The human body is not a cylinder, obviously. The differences between the relationships among chest, waist, and hip circumference strongly affect how a garment fits, moves, and provides protection. Garments must therefore accommodate body proportions, not simply overall dimension. Moving on to the importance of the body proportions, one issue I have seen repeatedly in factories when I myself went there to talk with workers and do fitting sessions is that a jacket may fit a woman around the chest and waist but fail to close around the hips. Here, bottom circumference or hip circumference means the largest circumference around the hips and the buttocks. I have seen many women try on jackets that fit very well through the chest and waist but could not be closed at the bottom. They were forced to move 2 or even 3 sizes up, leaving the rest of the jacket excessively large. You might ask why hip circumference matters for a jacket, right? The thing is that in workwear and PPE, the jacket often needs to extend far enough down the body to maintain protection while the wearer reaches upward, bends, or crouches. If the jacket cannot close properly around the hips, it cannot perform as intended. Chest, waist, bottom circumference, and sleeve length are therefore important starting points for jacket fit. Other measurements, such as shoulder width, armhole dimensions, biceps, and forearm circumference, can provide additional detail when needed. Moving on, women are not one body type. The challenge is more complex than creating a single female fit, because women do not represent just one body type. Effective women's PPE must accommodate a broad range of shapes, proportions, and sizes. This diversity exists among men as well, but however, traditional workwear size systems were largely developed using male populations, so men tend to be better represented and more effectively by those systems. The same diversity, therefore, creates a greater practical gap for women. Now, we will move to section 3, where we will talk about how people can be scanned or be sized with AI. So let us now look at how modern AI can improve individual sizing. Today, lengthy fitting sessions and manual tape measurements are no longer the only options. And when I say AI here, just to be clear, I'm referring primarily to machine learning and computer vision, like algorithms trained on numerical and image data to estimate body dimension. I'm not talking about LLMs or other meaning for modern AI. A typical process begins with basic information such as height, weight, age, and gender, and the user follows simple instructions to establish suitable scanning conditions and receives real-time audio and visual guidance from a virtual assistant. The system then captures two fully body images with a smartphone or maybe with a tablet and automatically extracts the required body measurement. This digital process is also more consistent than manual measurement, which can be affected by technique, recording mistakes, and transcription error. Moving on from images to sizing decisions. Extracting body measurements is only the first step. The images are securely uploaded for processing and the AI extracts the body measurements. Those measurements are then stored in a centralized dashboard. Next, they are combined with garment-specific sizing information, not merely a generic size chart. Then, finally, specialized recommendation algorithms identify the most appropriate garment size. Why is this important? Is because this creates a traceable digital workflow from image capture to practical sizing decision while reducing the opportunities for manual error. Now, we will talk a bit about Esenca Sizing, which is an example of AI body measurement solution. Esenca is one example for this type of modern body measurement solution, and our primary areas of focus include workwear, PPE, and medical applications, particularly compression garments for the medical applications, where accurate leg measurements are critical. This experience has enabled us to support large-scale workwear and PPE deployment. For example, a factory with thousands of workers can scan its workforce over a matter of hours or days instead of weeks. Workers who are absent during the scheduled session can receive a link and complete the process later, either at home, preferably in a controlled place environment, depending on the client's requirements. Our key capabilities include automatic body measurement extraction, realistic 3D avatar generation, support for virtual try-on applications, and automated garment size recommendation. So the scan can therefore support much more than a single sizing decision. Going forward, what makes an AI body measurement solution successful? We have been developing and deploying this technology for more than 6 years, and as an interesting coincidence, we began work on the solution on February 29, 2020, just before pandemic lockdowns made remote processes especially relevant. So just before the pandemic and on a special day of 29th of February. Through those years of development and collaboration with workwear companies, we identified 5 essential requirements for an effective body measurement solution: accessibility, guided image capture, measurement accuracy, speed, and garment calibration. The next 2 slides explain those requirements in more details. First, the process must be accessible. We all know the friction involved when someone asks us to try a new application, download it, install it, create an account, verify the account, and then learn how to use it. Now imagine asking thousands of workers to complete that process. This will never happen. For the end user, the experience should therefore be web-based and require neither an installation or an account. The company managing the deployment can have access to the administrative dashboard, but the worker should only need to open a link or scan a QR code, follow the guided process, and finish within 1 or 2 minutes. Second, the image capture must be actively guided. We cannot assume that every user will carefully read and remember tutorial. As you know, most of us skip tutorials whenever we can. Like just click next, 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 yes, yes, yes. A virtual assistant should provide audio and visual feedback during capture, guiding each user into the correct pose and position. This standardization produces images of consistent quality under comparable conditions. The next requirements that we discovered over the years are measurement accuracy, speed, and garment calibration. So measurement accuracy is essential, obviously. Reliable size recommendations require precise individual measurements, but accuracy at the individual level is not the entire story. We also need high quality anthropometric data to understand the broader population, and we need a reliable method for matching each body to the garment. Population data should be refreshed periodically. Small changes may appear over 5 to 10 years, while larger shifts can become significant over several decades. Identifying those changes early allows manufacturers to plan rather than react after their size systems have become outdated. Digital scanning makes this type of research increasingly practical, with appropriate consent and privacy safeguards that, of course, we all have to take into consideration. Measurements collected during deployments can contribute to an up-to-date understanding of the population. Speed is equally important. Workers should be able to enter a controlled scanning area, complete the process, and return to work with minimal disruption. In our solution, the full user journey generally takes 1 to 2 minutes. Image capture takes roughly 20 to 30 seconds, depending on how quickly the user follows the guidance, and measurement extraction itself takes about 1 second. So most of the time it takes is for the user to fill in the data and read the tutorial and so on. Finally, there is the garment calibration, which is the cherry on top. Body measurements alone are not sufficient. We cannot simply compare a person's measurements with a size chart and select the first size with larger numbers. Garments differ in elasticity, pattern construction, padding, rigidity, intended ease, and many other properties that may not appear in the size chart. For this reason, we develop a garment-specific calibration for each client. It models the relationship between body dimensions and the way each physical garment actually fits, allowing us to recommend the size that works best for that body. Now we come to anthropometry, at the part where I will geek out a bit, so I will get to be a little more technical, but I will try to keep it as short as possible. However, this is important to understand the actual data. Now, what is anthropometry? Anthropometry is the scientific study of human body dimensions and proportions. It can include height, limb lengths, circumferences, body shape, and many other characteristics. Its key advantage is that it provides objective data about the people for whom a product is being designed. The field is not limited to garments, footwear, or gloves. It also applies to anything designed around the human body, including chairs, mattresses, vehicles, bicycles, and medical devices or prosthetics. So basically anything regarding ergonomics. For workwear and PPE, anthropometry allows us to design for the actual workforce than for outdated assumptions. It reveals differences among populations, genders, and body types, and it helps us construct a size system that covers more people without requiring an impractical number of sizes. The goal is to maximize population coverage while keeping production complexity under control. In my personal experience, a size chart that provides a reasonably good fit for 90 to 95% of its target population is an excellent result. There will always be people outside the main distribution, and I am one of those people in our data set. Usually when we plot graphics, plots and so on, I am an outlier, and these cases can be addressed with specialized or custom garments. So, anthropometry forms the foundation of accurate sizing and better fitting PPE. We cannot design effective PPE without first understanding the people who will wear it. Now, moving on to the next slide, we will see a comparison between men and women in chest circumference. Let us examine the differences between men and women in the data. The histogram and density curve show the distribution of chest circumference in the two populations. Women are shown in light green, men in gray, and the overlap is in dark green. There is substantial overlap, although the women's distribution is shifted towards smaller measurements and has a somewhat different shape. The obvious conclusion is that men are larger on average. If we looked only at this chart, we might be tempted to believe that a women's size chart should be created simply by making every man's size smaller. The following measurements show why the conclusion is incomplete. Here we can see the waist circumferences, and the overlap is smaller and the difference between the two populations is more pronounced. Women's waist circumferences are substantially smaller on average. Even here, however, someone might still conclude that the pattern is the same as for the chest. Women are simply smaller and the men's dimensions can be scaled down. However, the next measurement changes this picture. When we look at the bottom circumference here, the male and female distributions overlap almost perfectly. Remember that these are the same populations that showed clear shifts in chest and waist circumference. Women have smaller chest and waist measurements on average, but their bottom circumference, or hip circumference, are comparable to those of men. The important difference is therefore not the bottom measurement in isolation. It is the relationship between the bottom and the waist and between all these measurements. This is one of the main reasons why size charts derived from men's proportions perform poorly on men. Now moving on to the next slide. This closer view makes the overlap in bottom circumference easier to see. It's basically the same histogram as before, but larger. Bottom circumference is one of the measurements with the greatest influence on fit for women's workwear. If a collection is scaled down uniformly from men's dimensions, it may become appropriately smaller at the chest and waist while leaving insufficient room around the hips. This is why a jacket may fit well through the upper body but fail at the bottom. Moving on, looking at waist to chest ratio, absolute measurements tell only part of the story, so we also need to examine proportions. This chart shows the waist to chest ratio, waist circumference divided by chest circumference. So women tend to have smaller waists relative to their chests than men. The difference between the distributions confirm that the two populations cannot be represented accurately by applying a simple uniform scale factor. The bottom to waist ratio also shows an even larger difference. For men, the average bottom circumference is roughly 10% larger than the waist. For women, the average difference is more than 30%. That is a substantial change in proportion, and it directly affects garment fit. There are, of course, individual women who will fit well in men's collections and individual men who may fit a woman's pattern. We are discussing population level trends here, not rules that apply to every person. At the population level, however, the difference is clear. The same garment geometry cannot serve both groups equally well. The scatter plots present the same data as before, but from a different perspective. Here, the chest circumference is on the horizontal axis, and waist circumference is on the vertical axis. We still see considerable overlap between the male and female clusters. So viewed alone, this relationship might again support the mistaken idea that women can be accommodated simply by shifting the men's sizes downward. Now, when we compare chest circumference with bottom circumference, the clusters begin to separate much more clearly. This is the relationship that a uniformly scaled men's pattern fails to capture. At similar chest dimensions, the required room around the bottom can differ substantially between the two populations. The separation is also clear when we compare waist and bottom circumference. More importantly, the difference is not merely a fixed offset. If we drew a trend line through each cluster, the lines would not be identical or perfectly parallel. Simply adding or subtracting a constant amount from selected measurements is therefore not enough. The underlying proportions and grading relationships also need to change. This plot continues the same analysis by comparing proportional measurements rather than absolute circumferences. Once again, the male and female populations occupy meaningfully different regions. Looking at ratios helps us separate overall body size from body shape. Two people may have similar absolute dimensions in one area while requiring different garment geometry because the relationship among their measurements differ. This final plot provides another view of the same underlying conclusion. Across multiple combinations of absolute measurements and ratios, the separation between the population remain visible. I will not spend too long on every statistical chart, but I want to emphasize that the conclusion is not based on a single selected measurement. It appears consistently across the data. Effective women's PPE needs patterns and grading rules derived from women's anthropometry. Now, moving to the final section, the future of women's PPE, we can say that the future of women's PPE rests on 4 pillars, at least that's what we believe. The first is accurate digital body measurement. So a fast, contactless and repeatable way to capture the anthropometry for each worker. The second one is dedicated women's collection. These garments should be designed from women's anthropometric data rather than adapted from men's size chart. The third pillar is intelligent size recommendation. Once a worker has been measured, we need a validated method for matching that body to the most appropriate size in each specific garment. The fourth and final pillar is a connected digital workflow that brings the entire process together, from measurement and recommendation to ordering and garment delivery, with as little friction, delay and manual work as possible. The future is data-driven. This may sound like a familiar phrase, and it is the mantra in the last 20, 30 years, but you have to believe me that in this context is especially true. Understanding population data is essential both for designing appropriate workwear and PPE and for providing accurate individual size recommendations. Better PPE comes from combining reliable anthropometry, purpose-built garment designs, and connected digital workflows. So the future of women's PPE is not simply about producing more sizes. It is about designing a practical range of sizes that fits a greater percentage of women, and then matching each worker to the right garment. There are many related topics we could explore further. We have studied garment shrinkage and found that a nominal shrinkage value can hide substantial variation in practice. Some garments may shrink by different amounts, while others may loosen after repeated washing. Different use cases also demand different definitions of fit. Firefighting PPE, for example, has strict protection and mobility requirements, while ceremonial uniforms may prioritize appearance because they are infrequently and in different conditions. Trust me, this was a problem that we encountered in practice with some of our clients. These examples reinforce the same point. Sizing cannot be separated from the garment, its use, and the population wearing it. Now, this brought us to an end. Thank you for your time. I hope this presentation has shown both why women's PPE remains a challenging problem and how anthropometric data, dedicated garment design, and digital sizing technology can help solve it. If anything in the presentation has sparked your curiosity, I would be very happy to discuss it in more detail and answer your questions. Thank you.
Thank you so much, Edward. That was very interesting, and you can tell that you're very passionate about what you're doing with all of the documents and data that you were able to share with us. So I do want to open that up for questions. So if you guys can, I was looking to see, I believe there might be a chat option if you want to post in the chat. And then otherwise, if you want to just come off mute and ask your question, we can go ahead and get that started as well. I did have a question to kind of get us going, though. I would, because understanding the trends, it isn't just about comfort. It really does, as you mentioned, impact mobility, productivity, compliance, and ultimate worker safety. What has been, I guess, what surprised you the most when you started getting involved with this research and doing this type of research?
Well, the biggest surprise was that the size charts do not tell the full story. As I said, if you take a person with 30 inches chest, they will not fit in the 31 inches size in the size chart. You will need a little bit of ease there. So basically, you need a mathematical function to go from body measurements to garment measurements. And this took us a little while to figure out, but that's why we have that dedicated calibration process. And I think this was the biggest surprise. Also, still related to this, we found out that the quality control is not always the best, and sometimes garments tend to go outside of size chart tolerances. And that's a bit hard for us because we are evaluated on how the garments fit. But if the garments are outside of the size chart tolerances, then we have bad data as input. So it's like moving sand all the time.
Very good. Thank you so much. I kind of got sidetracked there just a minute. I was looking. So Amy Rusa has a comment too. In the future, how do you see this helping manufacturers in the design process?
Well, it's not in the future. We already helped manufacturers doing this. Of course, small scale. When we scan people, we have the body measurements. Then we have the size charts. And then we find a formula between the body measurements to the size chart. And this is done via the physical garments. Now imagine that the size chart is not there. You can create the formula just by the body measurements and the physical garments that you try on. So basically, you can create the size charts based on people feedback by trying on the garments. One important note here, the people trying the garments should be workers, not office workers, plant workers, right? Because they know how the actual fit should be. And if you have enough people doing this, you can remove the outliers that have weird fit preferences and you can find this formula. And we did this for both garments because we had a client that said that had some problematic size charts. We proposed new size charts for them. And basically, they took the process from the beginning, created a new pattern, grading, and so on. And now they said, yeah, this makes more sense now. And another client, we did it for gloves, for handwear. They didn't even have a dedicated size chart. They had more like a measuring chart where you put your hand, you're last size 6, you're size 7. But we created dedicated size chart with lengths, circumferences, and so on. So, Amy, what you're saying, we are already doing it. It's more a barrier of producers willing to do this process because it's costly. You have to change your process. You have to change. I understand. And you see some guy from Europe telling you, hey, you need to change your garments. But if you insist and if you show the data and so on, there will be a person that will listen and will try to make a change if it is beneficial for them.
Thank you. Thank you. A follow-up to that is, do you have any case studies on how this affects how this has effective, I think it's supposed to be affected, employees' improvement at work? Do you have any case studies available?
Yeah, we have case studies. For example, with Meva, one of our biggest clients, we scan thousands of people and we have 97% accuracy for recommendation. So 3% return rate with our solution. And basically, they scan 30 to 40 people a day before with the fitting session. And now they are doing 300 to 400 people a day with this return rate. So we have that. We have Lavance in the Netherlands. We have Essity, which is a medical use case for compression socks.
Very good. Thank you. What was, you mentioned the medical sock. Is it Essity? Is that what you said? The name of that?
Essity is the company. Jobst is the product.
Okay. I'm familiar with that one. That's why when you said that, it was like, okay. So many of our members work closely with distributors. How do you think distributors can use the body measurement technology to improve customer satisfaction and reduce maybe exchanges or returns?
Well, there are multiple facets to this. If you want, let's say that the distributor, are not happy with the current collection. One collection is not working very well in practice, and it's not because the recommendation was bad. People don't find the size that actually fit them from the selection. If you have that problem, you can do an anthropometric study. We're already doing this with a European airline that have this specific problem, and they are scanning 1,000 people, basically their employees, and we will create suggestions for size charts and grading so they can improve the existing products. But there are many companies that don't have this problem. Their garments are okay-ish. It's more a matter of size recommendation. So you can use the flow that Esenca offers to scan the people and get size recommendation. So we reduced the return rate from 20-30% to 3-5% for many companies. I think you're muted.
I was. Thank you so much. Are there any other questions out there? We have a few more minutes here for question answer. And this is being recorded, so we will get this out to everyone that has attended. And if you have any other questions in the meantime or that you think of afterwards, you can always reply to the email. It's our Gmail email for AWSAM is AWSAM org, O-R-G, at gmail.com. So awesomeorg at gmail.com. But Thank you, Edward, for a very interesting presentation, and I appreciate you putting everything together. And Anna, yeah, you just said the same thing. Thank you for putting this together. And this was a great kickoff to our educational webinar series. So thank you so much, and everyone have a wonderful day.
Thank you. And don't forget, if you have any questions or want to have a more detailed chat, you can contact me via email. More than happy to discuss how we can improve PPE.
Can you give us your email real quick, Edward, so we have that?
Yes.
I can share it in the
Uh,
email, but just in case somebody wants to jot that down right now.
I wrote it in the chat. It's edward@esencasizing.com.
Great. Thank you. Thank you so much for that. All
Thank
right.
you.
Very good. Have a great day, everybody.
Have a great day. Bye-bye.
Bye-bye.